Okay, so we're going to look at section 5.5 this time. And this is another integrating thing that we have to do. This is called the substitution method. And so here is the idea, okay? Okay, so the concept here is, okay, we're kind of doing what we would call a chain rule backwards, okay? Sometimes, and guys, if you've ever seen me do a substitution method, I use the letter U. This is kind of where that stems from, because oftentimes this is called a U substitution, okay? So what we notice here, when we think about derivatives, especially when we think about chain rule, the answer has to have the derivative of the first thing, okay, and the derivative of the inner part. Think about derivative of the mama times the baby left alone, or derivative of mom with baby left alone, and then derivative of the baby. You have to have the baby on there, okay? So what we notice here, okay, is we've got this this x cubed plus x, and this part looks like the derivative of that. So what we do is we're going to let u be x cubed plus x, okay? Then du dx, the derivative of u, is now 3x squared plus 1, okay? And then solving for du, we have that is 3x squared plus 1 dx, and we'll stick that in a set of parentheses. So now if I rewrite what we have up here, I now have the integral of u du, u to the fifth, okay? Now notice, I really focused on what is this the derivative of? Well, it's only this inside part. So the only part of this that I'm changing is the u to the fifth. Now, if I integrate this, we know that this integrates back up to 1 over 6 u to the sixth plus a constant. And then we push this backwards and we re-put the u back in place. So it'd be 1 over 6, equals x cubed plus x to the sixth plus c, okay? And this winds up being our answer. Now, the part that's going to be challenging is making sure, okay, that we see and recognize what we have the derivative of, and then make sure that we do the appropriate replacement, okay? So let's take a look at another one, or actually I'm going to take a look at the ruling here, okay? So if you have the integral of f of g of x with g prime of x dx, okay, so think about this last one. The g of x function, the inside function, was that x cubed plus x, okay? So think about that last example. G of x would have been x cubed plus x, because g prime of x was that 3x squared plus 1. Our f of x was x to the fifth. It was that fifth power that was sitting on that thing, okay? If you have this setup, okay, then what we're going to redo is that this is the integral of f of u du, okay? We are going to do that replacement with the u thing, okay? Now, steps to doing this, okay? We got to get g of x to be u, okay? We need to get du dx needs to be g prime of x. Now, most of the time, we're also going to have to do this. So du is going to be g prime of x dx, okay? So now, looking back at this original, we're going to have, so then we're going to integrate, okay? So we're going to integrate some sort of f of u du thing, okay? Well, we're going to have put u back into another function or whatever else. Then, once we've integrated back up, we're going to come back out of u and back into x, okay? So let's take a look. This method is something that it just takes practice, okay? It is not something that you are just going to jump on, okay, and see automatically. Okay, so we've got secant squared of 5x plus 1 times 5. Okay, now, first thing I notice is the 5 is the derivative of that chunk. So that means u is going to be 5x plus 1. Du dx is going to be 5. And then I'm going to solve for du. So now I'm going to replace, and I'm going to have secant squared u. So I had the secant squared because I didn't mess with that. That's u du. My 5 dx is my du thing, okay? So now, secant squared, okay, is the derivative of tan. So this is tan u plus a constant. Again, I'm doing the plus a constant because I do not have boundings on my stuff. Now I'm going to finish replacing back. Tan 5x plus 1 plus c. Okay? And guys, if we think about it, just kind of process through chain rule. We would do derivative of tan, which is secant squared, times the 5x plus 1 left alone. Derivative of 5x plus 1 is 5. Okay, so you can kind of check yourself by doing the derivative back down and making sure that that's what was in your integration beforehand. Okay, so now sometimes, okay, what happens is, let me get this example up here and then we'll look. Okay, so now, first thing that I think of is I'm going to let u be the 7 theta plus 3. That means du d theta is equal to 7. Now, here's the problem. I need d theta, okay? I need to have d theta over here, okay? I don't have this 7 running anywhere in this, okay? So what we do here is, and I'm going to do this kind of in 2 steps, okay? I'm going to bring that d theta over, but I just need the d theta. This is going to be 1/7 du equals d theta, okay? So now, looking at our integration, and this is because they didn't give me my 1/7 that I need, or they didn't give me my 7 up here, so I'm going to have to create it, okay? So I'm going to have cosine of u and then 1/7 du, because again, this d theta is this part over here, okay? So I solved it out. Now, I'm going to bring the 1/7 out in front. So now this looks regular. Now, cosine comes from sine. So this is now 1/7 sine u plus a constant. And now I'm going to replace out 1/7 sine 7 theta plus 3 plus a constant. Okay, now again, processing that through. Derivative of sine would have been cos. Derivative of this would have been, with the inside left alone, derivative of this is 7 times the 1/7 that was up in the front up here, cancels off, and notice that's where this goes away, okay? Because otherwise I would have had a 7 coming into this original problem, okay? So sometimes we do have to do a little bit of slight modifications, okay? So let's take a look at the next one, okay? Now, this looks scary. Calm down. Sorry, let's switch that a little bit. Okay, looks scary. Guys, first thing I notice, x cubed, x squared. That tells me kind of where this is going to be. So I'm going to let u be x cubed. Du dx is going to be 3x squared. Okay. Pulling this all over to one side, I've got 3x squared dx. Now look at what we've already got. I've got the x squared and the dx, so I need those two pieces. That means the 3 needs to come back across. So 1/3 du equals x squared dx. Okay, now we only do this little trick with the numbers. Okay, like you're not allowed to like divide an x back through or anything like that. Okay, so now looking at what we've got, I have got, now I'm going to put the x squared and the dx all kind of back at the end. So I've got e to the u 1/3 du. Okay, I'm going to pull the 1/3 out in front. Now we talked about e to the u or e to the x we like because it just derives down to itself and integrates back up. So this is 1/3 e to the u because it just goes to itself plus a constant. And now doing our other replacement, that's going to be 1/3 e to the x cubed plus a constant. Okay, and again, thinking about this, if we did the derivative of this, I'd have 1/3 e to the x cubed, because that would just go down, times 3x squared. The 3 against the 1/3 would go away. The x squared would still be sitting, and that's what we've got up there as our function. Okay. Now, this next one is a little bit more challenging, okay? Just because of the way that it is kind of set up. Okay, so we've got integral of x square root of 2x plus 1 dx. Okay. Okay. Okay, now, logic says, okay, underneath here, okay, and guys, this one really is kind of a lovely, okay? So, logic says u is going to be 2x plus 1. That would be this chunk underneath the square root. That means du dx is going to be 2. Well, what the crap? I've still got this x sitting up here in the front. Okay, calm down. We're going to handle this, okay? Du is then 2 dx, but I don't see any 2's in here, so we're going to pull that back across. Sorry. Now, in order to get the x over here, we're going to solve this original thing right here, this original substitution for x, okay? So I've got u minus 1 equals 2x. I have 1/2 u minus 1 equals x. Okay. Like I said, this one's a little bit weird because of that extra thing. So now, what do we have in the replacement? That is 1/2 u minus 1. That is square root of u. And then 1/2 du. Okay, so let's make sure we track where all that came from. The x up here in the front, we said was the 1/2 u minus 1. Then I've got square root, because I haven't dealt with that. Square root of the inside we said was u. And then dx we said was 1/2 du. Okay, so I'm going to pull the 1/2 and the 1/2, and that's going to make 1/4. Okay, and then that's going to leave me u minus 1. And I'm going to go ahead and switch this to a 1/2 power. Okay, now at this point in time, we can distribute or, this in here. So I've got 1/4 u to the 3/2 minus u to the 1/2 du. Okay, like I said, this one's a little funky. Okay, so now I've got 1/4 coming back up. Okay, this is going to go to, if I add 1, okay, which is 2 halves, it's going to go up to 5 halves So I need a 2/5 in front, okay? We remember we talked about those reciprocal things. Minus, this is going to go up to 3/2, so that needs to be 2/3 plus a constant, okay? So now I'm going to push this 1/4 in. So that is going to be, let's see, 2/20. So that's going to be 1/10 u to the 5/2 minus, that's going to be 2/12. So it's going to be 1/6 u to the 3/2. Okay. And then now, because we don't know what this constant is, when I do 1/4 times that constant, we can still just leave it as a constant, okay? We don't have to try and push that out, okay? So now, doing the back replacements, okay? Doing our back replacements, we've got this is 1/10, 2x plus 1 to the 5/2 minus 1/6, 2x plus 1 to the 3/2 plus a constant. Okay. Now again, that one is a little more challenging. And the question always is there a better way to do it? No. Okay. Because if you thought, what if I shoved this x back in here? Okay. Kind of like tried to push it back in. The problem is then whatever you set your u as, you're not going to have that derivative. Okay. Because if this x went back in, it would go back in as an x squared. So then I would have like 2x cubed. Well, when I take the derivative of that, I'm going to get an x squared. I don't have an x squared sitting around in that problem, okay? So this is one that is a little more challenging. When you get like extra letters that show up into play, you may have to solve the original replacement for that letter, okay? To try and clean that out just a little bit. Okay. Okay, so looking at another one. Okay, we've got the integral of sine squared x dx. Okay, now this one is one of those instances where we are going to have to use some of our trig identities, okay, to make this happen. Okay. Okay. So thinking about this, okay, first thing that I'm gonna do, okay, one of the definitions for sine squared, okay, was that it was 1 minus cos of 2x over 2 and then dx. Okay. Now, I'm going to bring this divide 2, I'm going to bring it out to the front so that I've got something that is a little less. Okay. Now, the book does not show this, okay, because it's like a partial replacement, okay, that they do. So basically, okay, what they do kind of over here off to the side is they say if u was the 2x, du dx would be 2, doing kind of that same stuff that we've done before. 1/2 du equals dx, okay? But that only applies to this part, okay? So one of the things that you will sometimes see them do when you break this up, okay, is you could look at this as okay, I'm going to kind of break this up here, okay? Now, 1 integrates back up to x. So this is 1/2 x. Okay? Actually, I'm not going to do that yet. Hang on. I'll pull that idea here in just a second. Integral, okay? This is going to be cos u 1/2 du. Okay. I'm going to let that 1/2 come out here to the front, so it's going to be 1/4. Okay. So now, talking all of my little integration pieces back up, this is going to go back up to x. That's 1/2 x minus 1/4. Okay. Comes from sine. So this is sine u. Now, the little bitty piece that came from here and the little bitty piece that came from here, we can bundle all together into one big constant, okay? So now this is going to be 1/2 x minus 1/4 sine 2x and then plus a constant. Okay? So 1/2 x minus 1/4 sine of 2x and plus constant. And again, if you separate these, the little constant, you can call it like C1 and C2 that you would get here, you can put them all together into one big constant for there. Okay? So, look at another one here. Okay. Okay, so let's look at the integral of e to the x plus e to the negative x. There we go. Sorry. Okay, now, here is the concern. First off, I see this kind of, they've written the dx up here, okay? Even if they had that sitting out to the side, okay? That is 1 over. This starts to feel a little like natural log, okay? Or one of those other special patterns that shows up, okay? The problem is the denominator is kind of messed up, okay? So I'm going to do a little trick, okay? And this is a trick that we see done every so often. I'm going to multiply by an e to the x over e to the x. Now, e to the x times e to the x is going to be e to the 2x, okay, because we're going to add those exponents, or you would add your exponents, okay, and then e to the negative x times e to the x, those exponents are going to add. Negative x plus x is 0, e to the 0 is 1, okay? So now, I'm going to let u be e to the x, which means I got a u squared down here, okay? U squared is e to the 2x, okay? Now, let's talk. Du dx, derivative of this is e to the x, so du is e to the x dx, okay? Now, there's a sneaky little trick in here. Okay, so let's talk about what this thing is. Okay, so let's look at parts. E to the x dx, we have right there, that's a du. Over. E to the 2x, that is u squared plus 1. Okay, now this is one of those trig back things, okay, that we had the little chart for, our little inverse trig things, okay? This is the setup, okay? This answer, and it actually looked like 1 over u squared plus 1, okay, is the inverse for tan, okay? So this actually goes back to tan inverse of u plus a constant, okay? This is where having those charts and stuff, and yes, I give you the charts, okay? Yes, I'm going to give you the charts for the test, okay? So now, taking this back, this is going to be inverse tangent of e to the x plus a constant, okay? Not super pretty. Okay. Now, couple of things that we need to talk about, okay? And this is using some of our trig ratios, okay, and use substitution, okay? So let's talk about this. Okay, guys, if we think about, and I'm going to do this one, okay, so that we understand it, okay? Tan is sine over cos, okay? Okay. If we let u be cos, du du dx, derivative of cos is negative sine x. Okay, so du is negative sine x dx. Okay. Okay, so now going back over here, we've got, we're gonna have to pick up a negative. Okay, sine x dx is du over u. Now I'm gonna pull and make this look a little more like what we've seen before. Okay, 1 over u, guys, you've got to just know that 1 over u goes back to natural log. Okay, so this is negative natural log, and you've got to take natural log back up to absolute value. Okay, it's just got to go back up to absolute value, because you can only take log of positive numbers, whereas cos could come out with negative values. Okay, now this is a little trick that they like to do here. Okay, I'll be perfectly content with this, but they don't leave it this way. Okay, what they do here is they pull their power rule for logs back into play. This winds up going back up to here. Okay, so they bring this back up into, okay, and then they go, okay, but that's natural log of 1 over u plus constant. Okay, now I'm going to backtrack this. Okay, this is going to go to natural log of 1 over cos I'm trying to move my stuff over here, plus a constant. Guys, 1 over cos is secant. Okay, this is the answer that they're going to go for. Okay, so the integral of tan x dx is the natural log of the absolute value of secant x plus a constant. Okay, and they have several others. Okay, I'm fixing to list them for us here real quick, that are all done very, very similarly. Okay, so the integral of tan x dx is the natural log of secant x plus a constant. Okay, the integral of cotan x dx is the natural log of sine x plus a constant. The integral of secant x dx is natural log of secant x plus tan x plus a constant. And the integral of cosecant x dx is negative natural log absolute value of cosecant x plus cotangent x plus a constant. Okay. Okay. And these are ones, okay, that, you know, as there's a lot of little algebraic manipulation that is happening in these, that these occur. Now, these are formulas that I provide for you. Okay, like when you get ready to do your test, I give you these four. Certainly, if you needed to have one of the ones for those little trig identities, I would certainly be giving you those. Okay, I'm not going to like not give you some trig identity that's essential for solving a problem and not just hand it to you. Okay, like I'm not going to do that to you where you don't get to have that problem. Okay, so this is the end of 5.5. I hope this helps out. We do have to cover 5.6, so I'll have that video coming up shortly. And then we've got a few sections in chapter 6.